Swayam Prabha. Digital India. Educated India.
So we'll discuss today also on hypothesis testing, and this is the last lecture on hypothesis testing. Test for single proportions. This is what we have not really discussed, but there are situations when we want to test the proportion, that is, whether the proportion of times an event has occurred in independent trial is equal to a specified value or not. Whether the proportion of faults generated in a process is equal to a specified value or not. In the textile processes, many times faults are generated. Like suppose in a manufacturing facility of garment, if we produce 1,000 garments and when the garment goes for an inspection, they may find that some garments are defective and therefore they are faulty. So a daily record is maintained, and the proportion of faulty garment that is produced by a line, suppose based on the previous month, may be compared with the proportion that we generate today. So a specified value of proportion could be there, which could be maybe a standard value in some situations. So we want to test whether the proportion of faulty items, whatever it is more or less than the standard specified proportion value or not. Therefore, this kind of test we have to do, and hence we say that we have to test the null hypothesis. In this case would look like this. There's P dash is equal to P0. So P0 is the specified value, is the standard value, and P dash is the current value. So null hypothesis says there is no change, or P dash is equal to the P0. The alternative hypothesis can take three different forms. One is P dash greater than P0, or it could be P dash less than P0, or it could be P dash not equal to P0. These things we have already learned earlier. So alternative hypothesis could be either this or this or this. Let us say a sample of size n has been examined. It could be shorts, and x0 times the event has occurred. The event in this case could be some kind of faults, button missing or misstitch or anything, the way a short can be defined as faulty short. So let us say that a sample size of n has been examined and x0 times the event has occurred. The number of occurrence of the event in n independent trials would be expected to follow binomial distributions. You have to look back the binomial distance which we have discussed earlier. This is a very fit case of applying binomial distributions. And in any binomial distribution, the mean is mu is equal to np0, and standard deviation is root over np0 in 1 minus p0. We can also call it np0q, q0. Now these are already known to us, and we have already discussed about binomial distribution earlier. What is the mean value of binomial distribution and what is the variance or standard deviation of binomial distributions. So this is also a fit case of binomial distributions, especially when the sample size is large. Then binomial distribution can be approximated by normal distributions. Binomial distribution is basically a discrete distribution, but in situations where n value is very large, then binomial distributions can be approximated by normal distributions, and we can follow the normal distributions properties to calculate the probabilities. Therefore, this sampling distribution of number of occurrence of the event can be described, as I said, by normal distribution, which looks like this, where the mean of the normal distribution will be np0 and standard deviation is going to be np-1 minus p0. The significance level is the probability of getting occurrence greater than x0. So x0 is the number of occurrence of the events that we have observed. So significance level is that the occurrence will be greater than or equal to x0. That means it is basically the area that is shown in this curve, not the shaded area that is shown in this curve. Area is the whole curve. The shaded area, we have represented this area by alpha. So alpha represents this. Therefore, the significance level is the probability of getting occurrences more than or equal to x0 when null hypothesis is true, and this is equal to alpha as shown in this graph. Now if I want to find out this area alpha, what we need to know? We have to find out what is the corresponding value of z here. How much is the value of z here? And we know this formula also we have learned already. Z is x bar minus mu. So this is what is mu divided by sigma. This is what is sigma. So that will give us the z value at x0, that is the observed x. Once we know this value of z, now we need to consult the standard normal distribution table. So if we go to z table, then for a given value of z, we can find out what is the area on the right side of the z value. That means we can find out what is my z alpha and what is z0. So this is the observed value of z that we get, and for a given value of alpha, we can find out what is the corresponding value of z, where alpha will be predefined as a level of significance. So for a given level of significance, which could be 0.05 or 0.01, we can find out what is the corresponding value of z. That is what is, we say, z alpha, and whatever z value we observe from the current data that we get by doing the experiment, that is what is my z0 or z observed. Based on the criteria shown in the table now, the 9 hypotheses can be either accepted or rejected. And what is the criteria? The criteria is given in this table. If the alternative hypothesis is P is greater than P0, then the null hypothesis will be rejected, provided the Z is greater than, Z means here ZO, that is Z observed, or you can say the calculated value of Z is greater than Z alpha. Alpha is the level of significance. So depending upon the alternative hypothesis that we propose, we cannot have all the three hypotheses simultaneously. We will have either this or this or this. In a given situation, we will either have alternative hypothesis could be P greater than P0, or P less than P0, or P not equal to P0. And in those cases, the corresponding rejection criteria of the null hypothesis is also shown. So in these two cases, this is basically one-tail test. Also, we have discussed about one-tail and two-tail test. Whenever we have not equal to sign, it automatically means it is a two-tail test. And therefore, here instead of writing Z alpha, we have to write Z alpha by 2. And Z alpha by 2, this is on the positive side, this is on the negative side, this is minus. So therefore, these are the three different, you can say, rejection criteria, or the moment I get the calculated Z more than Z alpha, we say reject the null hypothesis. So depending upon the alternative hypothesis, these are the criteria we have to follow, and accordingly we have to either accept or reject the hypothesis. And that is how we can test the proportions. Now we will discuss an example which is related to the proportion, and the example is here. If we read it, black and white fibers are mixed in the ratio of 2:1. So many times we mix fibers in order to produce some special shade. Like if we want to produce gray shade, we have to mix black and white in certain proportions. So in the textile industry, for spinning different types of shades, many times we mix fibers of different colors. Now let's say we are mixing here black and white, and the ratio is 2:1. A sample of 300 fibers were chosen from the batch and found to have 220 black fibers. Is the result consistent with the hypothesis that the batch contained correct mix? So out of 300 fibers, 220 are black fibers. So rest of the fibers are obviously white. So you have 80 fibers which are white. So the question that is raised is the batch contain correct mixture or not? So the solution will be proportion of black fibers is how much? 0.66. P is actually 0.66. So hypothesis, null hypothesis says there is no change. An alternative hypothesis says there is a change. So it is a two-tailed test. It is not saying whether it is greater than or less than. So alternative hypothesis is the way we want to propose it. We can propose the alternative hypothesis. So these are the two hypotheses in this present case. Now, from the data that has been given in the example, we find the value of x, observed value of x. What is x? X in this case represent the black fibers, which are 220. value of n is 300, total 300 fibers we have tested, and the value of P0 is 0.33. If we try to calculate this value of P0 should not be 0.33, it will be 0.66 because it is representing the proportion of black fibers which we want in the mixture, and that is what is 2:1. That means 2 by 3, that is 0.66. So this P dash is going to be this much, 0.66. P0 is what we have observed. Now the Z value corresponding to X0 220, we straight away apply the formula that we have seen in the previous slide. If we substitute the values of X and P in the equations of Z, we will get a figure of Z which is 2.68. So corresponding, the graph is shown here. The mu value is 198 because n into P is what is mu. So how much is n? N is 300. And P for this is 0.66. That is what we want to maintain. And if we multiply this two, this will give a figure of 198. Therefore, mu is 198. And the observed value after counting is coming, the value of X is coming to be 220. So that means X is somewhere here, mu is somewhere here. And the point is, whether sort of decision we will take if I get a X value which is 220, but the mu value is supposed to be 198. That means the mean value of the black fibers is around 198. Actually, exactly 198. However, by taking a sample and counting 300 fibers, we find the value to be 220. And hence, the decision we have to take whether the proportion is correct or not. And therefore, when we find Z value corresponding to this X, this Z value is coming to be 2.68. So that means Z here is actually 2.68. And the value of alpha for this Z, area of the curve which is beyond this, shown here by alpha, is only 0.0037. So level of significance is very, very low. In percentage term, it is only 0.37%, and hence the null hypothesis can be rejected. The batch does not contain, therefore, the correct mix. That is the conclusion that we are going to take in this case. Now we go to the next topic. Again, hypothesis testing, test for single variance. This also we need to test. What happens at times we are interested to know whether the variance has changed or not from the previous standard value. Variance means standard deviations. So it is a measure of variability. So many a time now variability goes very high in maybe count of yarn, maybe GSM of fabric, or maybe in ends and peaks. Ends and peaks per inch may not vary that much, but especially the weight or the other properties of the fabric or yarn may vary a lot. And we need to control the variation, and therefore we make certain adjustment in the process. It's these things I have already told earlier, and we need to only test the variance whether it has changed or not. So in this case, the null hypothesis would be that sigma square equal to sigma square 0. Sigma square basically means the variance. Sigma square 0 is the previously known value So original value, let's say, is sigma squared 0. This is the original value. Alternative hypothesis could be again sigma squared is greater than this, or H1 could be sigma squared less than sigma 0, or again double-sided or two-tailed test. The corresponding hypothesis could be sigma squared not equal to sigma squared 0. So these are the three different alternative hypotheses. The first one says that the variance has not changed. In this case, we are basically trying to say the present varies in more than the original. This one says present variance is less than the original. And the third one says there is a difference between the present and the previous variances. But it does not mention whether it is more or whether it is less. It just says that there is a difference. The difference could be on the positive side, it could be on the negative side also. Both. Let us assume that for a sample of size small n, that is, we take a sample of size n, and the variance that we calculated is a squared 0. We know that this particular ratio n minus 1 a squared 0 by sigma squared 0 follows chi-square distributions with k n minus 1 degree of freedom, provided the original distribution is normal. This was also discussed while we were discussing the chi-square distribution earlier, that n minus 1 a squared 0 by sigma square, whether you write 0 or not doesn't matter, n minus 1 sigma square by a square by sigma square follows chi-square distribution, where a stands for the standard deviation of the sample and sigma stands for standard deviation of the populations. Now, but this follows chi-square distribution that is already known to us. We need to calculate the observed value of chi-square. So we have to calculate now what is the chi-square value now, that is based on the experimental results. So observed chi-square value can be found out based on this ratio n minus 1 squared 0 by sigma square, and then compare it with the chi-square that is there in the table for a given value of level of significance. So therefore, the critical region for testing sigma square equal to sigma square 0 for normal population, the various alternative hypotheses are also listed here, and the corresponding rejection criteria are also given here. There is a similarity in all the cases. You will find that these are the alternative hypotheses and these are the corresponding rejection criteria. So from the table we have to get this value. Once we know the value of alpha, that is which will be specified, what is the level of significance, we can find out what should be the chi-square alpha or chi-square 1 minus alpha. In this case, you have to look back the chi-square table and you have to learn how to read the chi-square table. So the observed chi-square value must be compared with the table chi-square value, and based on the alternative hypothesis we have to do the comparison and reject or accept based on these three different criteria. So based on the criteria shown in the table, the null hypothesis can be accepted or rejected. This is the simple small theory. So a lot of similarities are there in the theories, Now, if we do a calculations of this based on an example, it will be much more clearer. And the process steps are mostly same. Let us say a golfer is playing 10 rounds and average 71.3 with standard deviation 1.32. Test null hypothesis that the consistency of his game is actually measured by sigma 1.20 against alternative hypothesis that he is less consistent. So we are basically comparing the variances here. So these are the two corresponding hypotheses. One is no change, the other one is less than what he was having earlier. So n is 10 in this case. So how much is chi-square value calculated in this case? It's better to write chi-square calculated because this is calculated based on the data that has been given to us. So we calculate the value and we get the figure, this 10.89. And now you have to go to the chi-square table for a level of significance 0.05, which is stated here. We have to find out, and for the degrees of freedom 9, because it is 10 number of samples are there, so the degrees of freedom will be n minus 1, that is 9. We have to find out what is the chi-square value from the table, and that value is 16.92. So this is the table value of the chi-square, and this is the calculated value of chi-square. So what we see, this value, calculated value, is less than the value quoted in the table. That is chi-square observed or chi-square calculated is less than the chi-square from the table. And therefore, we say null hypothesis cannot be rejected. It has not gone beyond this value. As long as the observed value or calculated value of chi-square remains less than this, we will say there is no difference at the level of significance 0.05. If it crosses this value, if I get a value which is 18, 19 or 17, then we'll say the null hypothesis has to be rejected then, and we'll say there is a difference now. So it all depends whether the value is less or value is more than the value of the chi-square based on the level of significance that we can find out from the table. So if we have a chi-square table, you must check if your chi-square table, keep it in front of you and find out that at the level of degrees of freedom 9 and 0.05, what is the corresponding value which is quoted there. This is another example based on this hypothesis testing of variances. The thickness variance of a non-open sheet was known from past data to be 0.18 inches square. A change in the process was initiated and the thickness of 101 samples were measured. Again, the variance was found to be 0.13 inches square. Test at 0.05 level of significance whether the process change has made a difference. Assume normality. This is the question which is asked. So the steps are exactly same. We find out what is the value of chi-square which is observed or say calculated. So this is the formula. We apply the values, we get a figure which is 138.4 chi-square value. And now we have to consult the table, chi-square table, level of significance 0.05. But degree of freedom is not, this will be 100 because it is n minus 1 is how much? N is 101, and therefore this degrees of freedom is going to be 101 minus 1, that is 100. So I calculate this chi-square and get a figure this much. It's a two-tailed test, so you have to find out what is chi-square 100, 0.025, and this figure will be coming around 108.13. And now we have to compare this data with this data. Who is bigger and who is smaller? Since this is more than this, and therefore we have to reject the hypothesis that H0, that is they are same. So it basically means by making some process modifications, the variance has really gone down from 0.18 to 0.83 to 0.13. It is not due to chance. So we'll reject H0. Test for differences between two variances. We may need to compare the variances of two populations, sigma 1 square, sigma 2 square, and the null hypothesis is whether these two are same or not. So this can be done provided the two populations are normal and the samples drawn are independent from these populations. The test method is based on now F distributions. So when there are two separate populations, both are normal, and we draw samples from both of them and find out what are their variances, then we want to compare between the variability in population 1 and population 2. Then you should go for like this kind of test. So we have seen earlier that the sample size N1 and N2 and observed variances are these two sample variances. So we have to find out this ratio. This was also done earlier, that S1 squared by sigma 1 square, S2 squared by sigma 2 square follow F distributions. And these are the degrees of freedom. If H0 is true, then this reduces to H0 is true means if sigma 1 squared and sigma 2 squared are same, then these two are same means they will cancel each other. So we will be left out with this. F is S1 squared by S2 squared, and this stands for observed values. the critical regions of the null hypothesis against different alternative hypotheses are also shown here. They are also stated here. This is how, in a similar fashion, we can write the alternative hypothesis and corresponding null hypothesis, rejection criteria of null hypothesis. These are the three different rejection criteria. We should always take larger value of either an or S2 in the numerator when you take the ratio. Now we come to another problem just to understand it further. Two samples are chosen from independent normally distributed populations. So population A is this and this. Population B, N2 is 13, S2 square is 36.4. So the variances are 47.3 and 36.4. Now the question that is raised, test at 0.05 level of significance whether there exists any difference between the population variances. These are the sample data. So solution procedure will be, the null hypothesis says there is no difference. Alternative hypothesis says there is a difference. So alternative hypothesis we propose not equal to, so they are not same. And we take the ratio. This ratio gives us a figure 1.29 F value. So observed F value is this, and degrees of freedom K1, K2 is also calculated, and now this is the typical F distribution graph that looks like this, and we have to find out that if at the 0 point level of significance, what is the value of F? So F, when you have, it is on both sides you have to check. This is a two-tailed test. So this side area is 0.025. The other side area will be also 0.025. And at the 0.025, we test it and get a value 3.18. So the table value is 3.18. The calculated value is, or observed value is 1.29. Now comparison is between these two. The F value is much less. The calculated value has come somewhere here, which is just 1.29. So it is much less than the critical value of F. So what should be the conclusion? That null hypothesis cannot be rejected because it is somewhere here, less than here. It is not falling on this side. This is how the calculation part is very, very simple. It's just only 2-3 steps. Hypothesis testing using p-value. This p is something we also need to know. It is also very simple. Once I go through it, you'll be able to appreciate immediately. P-value is the probability of getting its test statistic equal to or more extreme than the sample result given that null hypothesis is true. What it basically means, p-value is also known as observed level of significance. Observed level of significance is also, p-value is known. And the decision rule for rejecting H0 is if p-value is greater than alpha, then do not reject null hypothesis. If p-value is less than alpha, then reject null hypothesis. Or in another simple way of saying it, when if p-value is low, then H0 must go. Easy to remember. So lower p-value means null hypothesis to be rejected, and higher p-value means null hypothesis cannot be rejected. So we'll calculate now the p-values. Let us take an example. The time taken to complete a task by a sewing machine operator with the existing machine in a garment factory follows normal distribution with mean 4.5 minutes and standard deviation 1.2 minutes. Okay. Then a machine from another manufacturer was brought for trial. It was found that the stitching time for 25 samples had a mean 5.1 minutes now. Use p-value approach to determine whether there is evidence that the population mean has changed. That is the question that is being raised. So a sewing machine operator, the sewing mean time earlier with one machine it was 4.5 minutes, standard deviation was 1.2 minutes. Then he is given a new machine or machine from a different, made by different manufacturer, some other make, and it is found to be that with 25 samples the average time came to be 5.1 minutes. Use the p-value approach to determine whether there is evidence that the population mean has changed or not. So we are comparing the means. So H0 is mu equal to 4.5 and H1 is mu equal not 4.5. We will find out what is the value of Z. Z value is plus 2.50. This formula is very well known formula. We substitute the values and get Z. Corresponding diagram is shown here, the Z value. So Z alpha by 2 is 2.50. So this area we need to know. This area. This is what we actually are interested to know how much it is. So we have to consult the table, Z table, to find out what is the area they have quoted. So that area is equal to 0.0062, which is basically alpha by 2. So alpha is going to be 0.0124. It is a two-tailed test. So alpha by 2 this side and alpha by 2 this side. Total is alpha. So alpha by 2 is 0.0062 and therefore alpha is 0.0124. So p value for the two-tailed test is going to be 0.0124. That is the value of p in this case. That is the area beyond the calculated value of Z. What about the calculate the value of Z from the data to beyond that Z? What is the area? What is the tail area that remains? That is what is your p value. So the tail area will be less and less. The further, the bigger and bigger is the Z value. The more is the Z value, that means this point will shift this side, this side, this side. So the area under the curve is going to be less and less and less. So lesser value of P automatically means higher value of Z. and that basically means the null hypothesis to be rejected because it is too far from the mean. Since p-value 0.0124, point will be here, is less than alpha equal to 0.05, we reject null hypothesis, and therefore we accept the alternative hypothesis which says that mu is not equal to 4.5. This one we accept, that they are not same. We only say that they are not same. So this is how we apply the theory that we have discussed while trying to find out the p-value approach we can adopt also to say whether the alternative hypothesis or null hypothesis is true or not. So p-value always means it is the area beyond the value of z. Area what? Area, tail area of the normal distribution curve, or not normal, the standard normal distribution curve beyond the calculated value of z. That is what is the value of p. And lesser the value of p, we have to reject the null hypothesis. So conclusion is population has changed from the previous value. Now this thing what comes is also important to, that is statistical significance versus practical significance. At times, due to large sample size, we may get result that is statistically significant but has very little practical significance. But even though statistically it is significant, the practical significance is not there. The practical significance is not a statistical problem but a technological or commercial question. That is what practical significance depends upon this. Similarly, due to small sample size, we may get statistically insignificant result even though the significance may exist. This can also happen sometimes. So these two things you have to remember: what is practical significance and what is statistical significance. Statistical significance could be there, maybe there when we go for very large sample size, takes very large, more than 100, 200, 300 samples, and then test, and we can show that there is a statistical difference between the means. But this statistical difference between the means may not be practical significance because the actual difference between them is so little that practically it does not is not significant at all. And sometimes also the sample size is, when it is small, we may have statistically insignificant results even though the significance may exist, that we may fail to actually catch whether significance is there or not because we could not take sufficient number of samples due to whatever reason it is. Sometimes if I do a lot of tests, we may find that the yarn counts, suppose we want to spin a yarn count of 30 texts on a machine, and after doing 200 tests we find the value something, and statistically it may say that we want 30 texts, suppose we get a value 30.5, and it may show by doing the statistical test that there is a significant difference between these two. But because of this small difference, 30 and 30.5, difference of 0.5, will this small difference really matter in commercial terms or not? That if I want to sell this yarn to my customer, and the customer has already given me a tolerance of plus minus 1 count or 1.5 count, then this difference has no commercial, no, from commercial point of view, this difference doesn't matter to me. Even though based on statistical analysis, we can say that there is a difference between what we intended to spin and what we are actually spinning based on the samples that we have collected and tested. So this may happen that as long as the tolerance given is more than what we find out by doing some test and then checking the significance level, it may not matter, because practically it does not matter if the differences are too small, or similar thing may happen for technological consideration also, that we need not to change the draft because the count has gone up, changed by 0.5 or 0.2 or 0.4 or 0.6. So that could be a technological considerations. So these are the practical significance, and so statistical significance could be there, but practical significance may not be there. And error in decisions. In hypothesis testing, there is a risk of reaching wrong conclusions. We may wrongly reject a true null hypothesis or not reject a false null hypothesis. So two types of error could be there. We call it type 1 error and type 2 error. Type 1 error is null hypothesis is rejected, that is H0 is rejected when it is actually true. By doing the statistical analysis or test, we reject it when actually it is true because of pessimistic large samples happens to have been drawn. The probability of making such error is equal to significance level, that is alpha. And the type 2 error is null hypothesis is accepted when it is actually false because an optimistic small samples has been drawn. The probability in this case is called beta, depends upon how different from null hypothesis the truth is. So when the null hypothesis is false, but we still accept it, then the kind of error that we make is known as type 2 error. So these are the type 1 and type 2 errors. If we put them in the form of a table, then null hypothesis is true, but we reject. Then we make error that is called type 1 error. When null hypothesis is false and we reject it, then no error is made. That is the correct judgment. And the probability of doing the type 1 error is alpha, that is the level of significance. And null hypothesis is true, but not rejected. That means there is no error in this case. So this will be no error situations. But null hypothesis is false, but not rejected. This combination is type 2 error. So we get an error here, this combination, and in these combinations. And probability of getting this error is normally represented by beta. So we have two types of error. Null hypothesis is true but rejected. Null hypothesis is false but accepted. Not rejected basically means accepted. These are the two types of error that we can commit. We will just give an example. Suppose the cholesterol level of healthy men is normally distributed with a mean of 180 and standard deviation of 20. And now, men with cholesterol level over 225 are diagnosed as not healthy. What is the probability of type 1 error? We read it again. Cholesterol level of healthy men is normally distributed with mean 180 and standard deviation of 20. So distribution is normal. Mean value is given 180 and standard deviation is also given. Now men with cholesterol level 220 and 225 and above are diagnosed as not healthy. In that case, what is the probability of type 1 error? For this, let us look at the solution of this. We calculate first what is the Z value. Because we need to know for 225, if I draw this graph, it's normal distribution graph, the mu is given 180 and the sigma value is given 20. So I want that if doctor classified the people with having 225 cholesterol level and beyond as not healthy. So these are the people who are not healthy from here to this side. These proportions of people are not healthy. And that though they belong to the healthy population, in that case, we find out what is the corresponding value of Z when X is 225. And that figure comes to 22.25, and the value of alpha for Z equal to 2.25 is 0.0122. This will be, you have to consult the table to find out this value. Standard normal distribution table will consult, will find out Z 2.25 and what is the value of alpha there, and that alpha is 0.0122. Therefore, type 1 error probability is 0.0122. So that is the, whatever is the area, that is the type 1 error. That is the probability, that is what it is. Now, let us, the second question is, at what level in excess of 180 should men be diagnosed as not healthy if we want the probability of type 1 error to be 2%? That we want the error to be 2%. In that case, what should be the level of cholesterol so that the error value is only 2%? That means if I draw the same graph, I basically do not know what is the value of X now. But this area is given 2%, basically means 0.02 alpha. 2% means 2 by 100, which is 0.02. That means the tail area has been given here. So corresponding to this value of tail area 0.02, what is the corresponding value of Z? From the table we need to know, and that value is shown here, 2.05. That is the value we get. So if this is the value of Z, I use the same equation and substitute the values. X is unknown to me. So this is the simple equation we write. and you get a figure x to be 2, 2, 1. So the value of x, that means, will be 2, 2, 1. That is what is going to be the value of x. In that case, the type 1 error likely to be how much? 2%. So this is how now we can calculate type 1 error, and for type 2 error we need to know the mean of the populations. Not the existing one, but if the mean has shifted, where it has shifted. Unless that is known, we will not be able to calculate what is the value of beta. That means when something belongs to a different population, not with the existing populations, it belongs to different populations. So if we have another populations, then we need to know what is the mean of that population. If that is given, then we can find out what is the value of beta. Otherwise, we will not be able to calculate the value of beta. So you need to know up to this much. With this, we conclude this chapters on hypothesis testing and significance test. Both are going together actually. And I also request you that you must not only read the textbooks, listen to the lecture and look at the slides, but at the same time you also try to solve some more numerical problems, and that is what is going to reinforce your understanding and your capability to solve the problems as it appears in any test. Okay, with this we close this session. Thank you.